I want to get through isosceles, equilateral triangle stuff today. It is not as heavy into the proof things as we have been this little bit. It's kind of like a little break of the proof, to be honest. We'll do more proofs and stuff like that again next week. Tomorrow, a half day. I know that some people might be gone, but it doesn't. Remember, it's a field trip type thing. So it doesn't preclude you from getting the homework. Homework for tomorrow, if you are not around, will be posted online, and it is expected that it is done by Monday. This is not going to be anything new. If it was, I'll have videos and all that kind of stuff as well. Excuse me. When we're working through this next section, and this is actually the right number from the book. I remember to look that up for you because it's different from the old textbooks and stuff like that. We're going to talk, like I said, about isosceles and equilateral triangles. I know that all of you, well, I mean, rephrase that from the second hour that they didn't know, but I'm hoping that most of you know what an equilateral, or sorry, we'll do isosceles first, what an isosceles triangle is. What's isosceles? Yes, sir. Wrong. Wrong. So we're 0 for 2 here, Miss Epps. What are you saying? Yeah, 2 sections. So when we're looking at what's called an isosceles triangle, an isosceles triangle has a set of sides that are congruent. When we talk about isosceles triangles, if I call this triangle XYZ is isosceles, if I say it's triangle XYZ and I call that an isosceles triangle, just like we have in the past, there are specific inferences. Remember when I talk about inference, like things you can take from it? There's specific inferences that you can make. It tells you right away that you know that you're going to have 2 sides that are equal. And if you know the lettering, this middle letter is always going to be the angle between the 2 sides that are congruent. Okay? This is called the vertex angle. Sometimes they might say triangle XYZ is isosceles with vertex angle Y. It's just giving you more information. Whenever they label out triangles, obviously you always have 3 letters. If it's isosceles, the middle letter will always be the one between the 2 sides that are congruent. By knowing that, you can automatically say that XY and YZ are the same. Vertex angle. It's called a vertex angle. It's the angle between the 2 sides that are congruent from isosceles. Excuse me. So when you have an isosceles triangle, you get the 2 sides that are congruent. Second hour, for some reason, they had a hard time with the idea that an isosceles triangle could be a right triangle, it could be an acute triangle, and it could be an obtuse triangle. It doesn't matter. It could fall into any one of those categories. Your angle measurements still all add up to 180. But the one thing that does happen with isosceles is that notice how you've got the 2 legs with the tick marks? Those tick marks are pointing towards what are called base angles. Those base angles are always going to be the ones opposite the sides. These guys are called base angles, and those base angles will always be congruent. So in an isosceles triangle, you always have 2 legs, 2 sides that are congruent, and then the 2 angles that face them, that are opposite them, are also congruent. Okay. So X and Z are called base angles. And remember, it doesn't necessarily mean that that triangle is always they're on the bottom. It could be on the sides. It doesn't matter how it's drawn. You could have a triangle and have those 2 here, and there be an isosceles. Those would still be considered base angles. It doesn't necessarily mean they have to be on the bottom. All right. You've heard some of those terms, I'm assuming? Maybe-ish.
One thing I do want to have and make sure that everybody has is this. One of the things that does come up, when we're talking about isosceles is that if we know that you have an isosceles, there's certain things that you can say. So it's not a bad idea to have it on our progression sheet in case it does come up. Like I said, we may or may not actually do a full proof out of this. We might try a little one tomorrow. Today is mainly going to be working with congruency statements and some algebra and stuff like that. We're actually going back to numbers. So when I talk about an isosceles triangle, it basically is this. If, then, or, if, then, that happens. If you have legs that are the same, two sets of legs that are the same, you're going to have two sets of base angles that are the same. You have two sets of base angles that are the same, you're going to have two legs that are the same. And remember that the base angles are what they call opposite from what the legs are, or the sides, excuse me. Talk about in terms of sides. Excuse me. Not terrible? Now, what about this then? What about an equilateral triangle? What is it? Yeah. An equilateral triangle creates that you have all sides that are equal. And then therefore all angles are equal. So equilateral triangles have all three sides being the same. And an equilateral triangle is a fancy isosceles triangle. If you think about it, if I cover up one of these, if I cover that up for right now, I have an isosceles triangle, correct? Which means that those two sides are looking at the angles that would be congruent. It's looking at this one and this one. Now, if I cover up this one, that's telling me that those two sides are equal, right? They have the same tick marks, don't they? Which means their base angles would have to be the same. So across from this one has a single tick mark, which means across from this one has to have a single tick mark. That's why that works. That's why that works. It's basically a long form of writing out that law of syllogism. I'm taller than you, you're taller than somebody else, therefore I'm taller than that other person. That was a long time ago. Okay? 5 is greater than 3, 3 is greater than 5, 5 is greater than 3, 3 is greater than 1, 5 is greater than 1. It's one of those things, okay? And when you have an equilateral triangle, you're automatically going to have what's called an equiangular triangle. They kind of mean the same. What do all three of those angles have to equal then? Well, when they add up, yes, they're going to add up to 180. What is each individual? Let me rephrase that. What does each individual have to add to? Or what would each individual angle be? 60. They'd be 60. So in an equilateral triangle, you have all sides are congruent and all angles are congruent. They will always equal 60 degrees. Okay. Now, will every equiangular triangle be equal to or congruent to every other equiangular triangle? Would every equiangular triangle be congruent to every other equiangular triangle? That's right. If they could all be equiangular, like Keith was just doing, he was just going like this, the angles can be the same, but the lengths of the sides can be different. Okay? That's just one of those things that shows up when you think about it. That's equilateral, which means it's equiangular. Well, if I do that, those are still 60. They're not going to be congruent triangles. They would be called similar triangles. Whole other ballgame when we get to, I think we go to similarity right before the end of this semester. So there's no proofs with any of it. It's a lot of ratios, and ratios are just fractions possible. So we'll get there. What's that? Well, they said how come? I was going to say because we don't need to do proofs on similarity. You can if you want, but we just don't really need to. So again, when we talk about this whole idea of equiangular, or equilateral, excuse me, let's throw that in there so we got that memo. You can flip it over. There's the other side. You're not the first person to realize that there wasn't another. Some people, most people are like, oh wait, I'm out of space. Flip it over. If you want, it doesn't matter. I just wanted to make sure you guys have that down just in case. Yo! Hi. What's up, Mackie? If all three sides are the same, then what? All three angles, yeah. And if all three angles, then all three sides. And each angle here, bless you, bless you, and every angle is going to equal 60. That's one of the things you can always take for certain if you have an equilateral triangle. No matter what the side lengths are, the angles will always measure out to be 60 degrees. Always, always, always. Which then allows, by doing stuff like this, and knowing how this stuff works in the relationships back and forth, you can kind of morph it into other stuff. For example, if I go back and talk about, what do you call it? Isosceles, I forgot what it's called. All right, you guys got this? I don't want to get ahead of you here. I go back to an isosceles triangle, and let's say I draw one out that looks awesome, like this. If I draw out an isosceles triangle, I know that my base angles are the same. We'll call this A, B, C. One of the weird things that can happen, is that if you draw if you draw an angle bisector of the vertex angle, so which one of those is the vertex? B. If I draw an angle bisector out of angle B, so if I bisect the angle here at B, what it does is that not only does it bisect this, it bisects down here. And it always creates a right angle. One of those weird things that happens when you have an isosceles triangle, and it's not that you're going to be doing proof out of this. This is more of an algebra thing, more of a numbers thing. Let me write this out a little bit better words. If the vertex angle isosceles triangle is bisected. Then that bisector is what we call the perpendicular bisector of opposite side. It's a lot of weird words for something that when we draw it out in terms of why this is important or how this actually happens, when I show you an example, the reason that we show you this quick little definition now is because, well, honestly, that definition allows us to create what are called special triangles. Special triangles allow us to create what's called trigonometry. This one definition takes something that seems so mundane and it creates an entire other realm of math, which is really weird that this one thing happens. So, I know a couple of you guys are finishing that out. When you guys are done writing this out, just put your pencil down and show you what happens here. If we go back and look at the equilateral triangle. An equilateral triangle is a fancier version of an isosceles. You guys okay with that? So what happens is, if I take the perpendicular bisector out of here, that angle up top becomes how much? Instead of being 60, they're both 30s, okay? So that's 30 degrees. That's 90 degrees, which makes this 60. Okay. Also, if you have triangles, another one for an isosceles triangle, it could be called what's an isosceles right triangle. If I have an isosceles right triangle, I have a 90-degree angle here. What does that make those other two what are called base angles? 45s, okay? Thank you. Makes these both 45s. Now, if I'm looking at all these angles here, there's only what? We have a 30 degree, 45, 60, and a 90. Those four angles create the entire basis to trigonometry. Everything you ever needed to learn about trigonometry comes out of these four angles. What happens is, and you'll get to this next year, (30, 45, 60, 30, 45, 60, 30, 45, 60. Now, that looks really weird. That's called the unit circle. As you go around the unit circle, you start at 0, 30, 45, 60, 90. What is it then? Was it 40? No, it's gonna, yeah, it's 122, or then it's 135, 150, 180, 210. So as you go all the way around a circle, you're going in increments of these special angles. Now what's weird is that this angle, this is where everything comes from. This angle here is 30 degrees off of the axis. This angle here is 30 degrees off the axis. It's just rotated to here. Remember when you're talking about horizontal lines? Horizontal lines are always what equals a number. Slope is 0, correct. But is it y equal number or x equals a number? You got a 50-50 chance, so you just got it wrong. So it's always y equals a number. What happens, though, as you come across these things, you have certain ordered pairs. The y value doesn't change. The y value becomes negative. The y value becomes negative. They think the idea of trigonometry is just reflection around a circle. It's really, really weird to think of it that way, but what that allows you to be able to do is you're going to be able to do this. You're going to be able to graph sound waves, sine curves. You'll be able to graph cosines. You'll be able to do all of that. And it's all dependent upon those four angles, a 30, a 45, a 60, and a 90. So when we start talking about the importance of equilateral and isosceles, the reason why we talk about it now is so that when we get to our unit on Pythagorean theorem, right triangles, stuff like that, in geometry, to give you the basic knowledge of, calculator flying around, I can look at real fast. So if you look at a calculator, you've got, those buttons that say sine, cosine, tangent. Not a 9-inch nail saw, it's sine. It's those buttons will allow us to figure out what all this junk means. But it all starts with knowing what's called a 30, 60, 90, and a 45, 45. None of this is going to be this year. This doesn't come to you guys at all this year. What we'll get to you guys this year is Pythagorean theorem. The basic idea of SOHCAHTOA. Next year, this is a giant chunk of Algebra 2. If you go into pre-calc, this is a giant chunk of pre-calc. Okay? This is where math goes crazy. You have to believe me. If you understand these two triangles, everything falls into place. It's understanding how this is created because it's the perpendicular bisector of the side. These are created because it's the diagonal of a square. But what you'll have to use this year with this is something like this. Can you solve for x and y? Can you solve for... Yes, ma'am. I don't. I'm sorry. Are you bleeding profusely? What's that? Come to see. Make sure you don't have it right back. Are you all right? I got scotch tape. Where's we at? Vertex angle by bisects. It is the perpendicular bisector of the side opposite. Okay. So let's walk through a problem where we use equilateral isosceles triangles to solve for missing angles, to solve for missing sides. Just by putting together a bunch of stuff that we've learned already and how angles match up, how many degrees are in certain things, and so on. So, looking at a problem like this, I see three types of triangles. What do you see? Equilateral, isosceles, and right triangle. Okay. So, when I'm working through that, there's only one of the triangles that I know for certain what all of my sides are. Which one do we know all the sides of? The equilateral. They're all going to be what? Plus. So I know over here that these are all 12s. Oh, single tick mark, which makes this side 12. Okay, good. Now, what do all these angles measure here? Those are all 60s. Are we okay with that? What's that box mean? 90. Okay. How many degrees create a line? Okay. Take out 90, how many are left? Take out 60, how many are left? 30. What is this angle right in the middle here then? 30. Everybody see what I'm doing here? We're just walking backwards out of it. All right? And here you have an isosceles triangle. You have an isosceles triangle with a vertex angle that's equal to 30 degrees. That means the base angles have to be equal. How many degrees are in this circle in a triangle? 180. Take out 30, how many are left? Okay. So if these two angles both have to add up to be 150 and they are the same angle, you get 75. You okay with that? Yeah. Well, you're going to be okay, right? That gives me here. Be all right? Now, I still have to figure out what the length of y is. This is where it's going back to the idea that it knows that you've taken math at some point in your life up to now, and it hopes that you might have remembered something about right triangles. What's the one giant theorem about the sides of a right triangle? Say it. What? Say it. You're close. Pythagorean theorem. Then say it out loud. In right triangles, you have a squared plus b squared is c squared. What they normally assume at this point in your mathematical career, you have seen the Pythagorean theorem at least once or twice. Even though we haven't defined it yet in class, there will be times, and I think this has happened before, where it's going to assume that you know how to figure it out. Okay? So remember, when you're working with the Pythagorean theorem, the value of c is always across from the right angle. It's the opposite of the right angle. It's always the longest line. The other two, they're interchangeable. So if I say that we have b squared plus 12 squared is 15 squared, well, that just means I have to solve for b by using my calculator. What's 225 subtract 144? And what's the square root of 81? 9. This is about as complex as this stuff gets. Which gives you this value of 9. This side was 12. What's 9 plus 12? 1. That's, sometimes you have to put together a couple of parts from things that you may or may not have remembered. So is it a bad idea to put the Pythagorean theorem in a square just so you know that it's there for you? Especially if you forgot it? By all means, this is like your holy grail. Okay. Might not be a bad idea. It might not be a bad idea to take a second and put this, let's put this little bit in there so that way you know what it is. Just to save it. Have it written down so that way in case it does come up again, you won't go, It wouldn't be a bad idea, especially if you forgot what it was. It would be a bad idea to make sure you have it with you. It shows up from time to time. Okay, it's one of those reoccurring things that at this point in time they assume that you know, even though you haven't defined it in a geometry class. They're still going to think that, oh, they've seen this before. It's like I kind of assume that you know how to add and subtract. No idea. P-Y-T-H. Sure, works for me. Now I got a couple more here. No, just a couple algebra stuff. Let's say in a problem like this, I ask you to find out what is the perimeter in geometry. A lot of times they're going to ask you extra questions off of the definitions and stuff that we do in class. That's what I'm getting at here. I'm letting everybody get caught up first. So when you go through ones like this, obviously in this case, what triangle is it? Is it equilateral or is it the isosceles? The equilateral, which means all the sides have to be equal. Now, that means that you have three separate algebra problems that you can set up. Does it matter which one?
No.
It doesn't. It makes no difference whatsoever. And I'll show you why. When you go through this, knowing that you're either going to have 12x minus 13 equals 2x plus 17, or 2x plus 17 equals 7x plus 2, or 12x minus 13 equals 7x plus 2. If you go through those, if you math correctly, you should get the same value for x each time. Hopefully. So a lot of two-step equations. Subtract 2x, add 13. We get 10x is 30. X is? Okay. Subtract 2x, subtract 2, we get 15 is 5x. Hey, what's x? Okay. Add 7x, add 13. I'm sorry, subtract 7x, add 13. What's x? There's always one person that you gotta get smart out. Or smart angle side to side. Did geometry there. Did I get the same value for x each time? Do you have to do it that way? No. Pick. If you know that's isosceles, you've got all those values, just pick 2. 2 out of 3. It'll always work if you math right. Yes, sir. Yes, sir. Just pick one set, and go from there. One thing to remind you, when you're talking about perimeters, perimeters don't always add up to 180. Those are the angle measures. Perimeters means you have to substitute in 2 times 3 plus 17. And you wind up with 23s all the way around. Okay? That gives you the perimeter, was 69 meters. Okay? Then you go from there. So let me give you a couple of problems. I think I already posted it. What's up real fast? It was on page. This is section 4.5. Yes, ma'am.
Okay. 7 times 3, 21. What number?
I want to show you real quick before it gets too long about how one of these problems sets themselves up. Let me pull it up here real quick. I hate how this thing times me out.
On these problems, and I'll blow this up so you can see this if you guys want to get a picture of it or whatnot. On these problems,
The first four are nothing more than what does each one of these have to equal. So segment VT, this segment VT has to be congruent to base angles of T and X, BX. That's what you're looking at doing. The next three, you're summing for X and Y. The next four, you're using this diagram on 4 separate occasions. So whatever information you throw in for 16, if angle L is 58, then angle LKJ, well, that angle could be different than when it winds up being 48. Okay? You just have to read it. You're just reusing that diagram. So you can do it that way or just redraw it 4 times. And then the last 3 are a little bit of those work your way around a problem type of questions. So I'm trying my best to get everything to fit. It didn't fit as well as I thought. Close enough for something. Okay. Yeah, if you want to get a picture of that real quick, so you don't have to use your Chromebooks later, go for it.
One of those, tomorrow we're doing basically the same stuff. We might actually talk a little proof here or there, but I think we might hold off proof because we have another long weekend. So.
Wait, what page is